gang. We're going to start talking about waves pretty soon here. And as you can see, we're transitioning. We're going from simple harmonic motion to the study of waves. And as I've written here, it's a lot of terms, a lot of words, but not that much math, not as much as we're used to. I'm going to start by imagining, or having you imagine, what if this weight hanging from this string was a child on a swing? I went to the playground earlier today and could have been doing this with my son. Suppose maybe he asked me to give him some energy. I could do this. And at the end of all that, I haven't really given him too much energy. On the other hand, if I'm smart about what I'm doing, meaning if I pass energy at the right time to the passenger on the swing, I might be able to get the kid going. So what matters here is not the amount of energy at all that I give to it, but rather, do I resonate with this hanging weight, which means to pass energy on time. This pendulum, because of the length of the string, has its own natural frequency. It's the frequency at which it vibrates on its own. If I match that frequency when I pass energy to it, I'll be able to resonate with it and have it build up energy and go higher and higher with each push. It's also possible for me to get the timing right by hitting it on alternating swings, meaning I don't have to match or have its resonant frequency matched. I'll get it going here first. I could instead hit it every other time, like right now, and then wait, and then right now. That's still resonance, because I'm passing energy to it when it needs it, or on time. When we were studying simple harmonic motion, we learned that the time period of a pendulum depended only on its length. If you look at these two pendulums that are next to each other, you can see, since they're tied together, they're coupled, which means attached, and they're capable of influencing each other. These two, though, despite being coupled, will not resonate with each other because their lengths are different. As you'll calculate later, the ratio of their lengths isn't correct for resonance to occur. So, if I pull this one back and let it go, you'll see that it's not passing energy to the other one at the right time. So the other one doesn't pick up any energy. It's just like the child on the swing who's pushed at random times instead of with the same natural frequency as it has. Now you'll notice that I have two coupled pendulums that have the same length, meaning that they should have the same natural frequency because they have the same time period of oscillation, which means that they can resonate. Meaning, if I start one of them, or give it energy, it will pass its energy to the other. This is an inanimate version of the choice that I made earlier when I decided to pass energy on time. You'll notice that I started the left one, and now the left one stopped. And now the right one, which received all the energy that the left one had, has passed it back because the right one's now stopped. Here are two identical springs, but they have unequal masses on them, which again, as you know from simple harmonic motion, means that they would not have the same time period to oscillate, because the bigger the mass, the bigger the time period to oscillate is. So the one on the left does not have the same resonant frequency or natural frequency as the one on the right, meaning it cannot pass its energy to the one on the right in the right time intervals. So if I get it going, the right one wobbles around, but it doesn't start bobbing. Now you'll see that we have two masses that are the same on two identical springs, which means, from what you know from simple harmonic motion, that their time periods match, which means that their frequencies match, which means if I give the left one energy, it can pass that energy on time to the right one, which means to resonate with it. And the left one stopped, and the right one had all of it. And then the right one stopped. So there they are, passing energy back and forth. Okay, he's going to go, but not with the right rhythm. Go ahead. Okay, it didn't pile up. Go ahead, do it again. Now he's going to pass energy to the log at the right rhythm, if he can stand on it. Come on, buddy.
Stop it! Stop punching! Stop it!
There, it's going pretty good now. That's resonance. Now we've got a series of coupled oscillators that will resonate with each other because they have the same frequency or same time period, because they're all tied together so that they have the same length to the wave. This is our first example of a wave. A wave is, at least by our definition, a coupled resonating oscillator, which sounds like a mouthful, but coupled means they're attached. Resonating means they're passing energy on time to each other. An oscillator is just something that goes back and forth. So, if I pull this one back, I'll give it energy. And we'll create what's called a transverse wave, which means that it vibrates perpendicular to the direction that the energy travels. So, here goes. You can see already that it's giving its energy to its neighbor. And that second to last one is trying to give energy to its neighbor. And maybe you can hear that it's tapping on the can. There it goes. So this is one property of a wave that we just illustrated. It's that waves transfer energy, but they don't transfer matter. And you can see if you look close, they all take turns stopping or having their share or more than their share of the energy. Now we're ready to transition from resonance to waves. This is really where we go from simple harmonic motion to talking about waves formally. We've already seen that waves can be defined as coupled resonating oscillators. We've already seen that waves transfer energy, but they don't transfer matter. For example, you saw a weight hit a pop can, which is a way of sending an amount of energy down a string or chain of pendulums, but no material substance actually made the trip from one end to the other. We'll now say that there are two types of traveling wave. One you've already seen, which is a transverse wave, where the direction of the vibration is perpendicular to the direction of motion. I tend to sketch that kind of a wave like this, as a little wiggle that travels along a string or a slinky or something like it. This is a transverse traveling wave. You'll notice a couple things. One, that its direction of oscillation, which is this way, is perpendicular to the direction that the energy travels, which is that way. Another thing you'll notice is that it flips over when it bounces off or reflects off of a barrier. That flipping over is called phase change. The other type of wave you just saw is a longitudinal wave, which is also called a compression wave, and it's a wave where the direction of vibration is the same as the direction of motion. Here, I'm drawing it as a slinky that is stretched out in front of and behind this little squeezed portion. Now I'm going to make a compression wave, which is also called a longitudinal wave. This kind of a wave travels in the direction that it vibrates in. Here, and you might not be able to see it all that well, I'm going to squeeze and stretch this spring material, and then when it decompresses, a wave is going to travel the length of the spring. These are the names of the parts or components of a traveling wave. The highest point on a transverse wave, highest meaning furthest from the equilibrium line, is called a crest. The lowest point, which is furthest in the other direction from the equilibrium line, is called a trough. The distance from the beginning to the end of a single wavefront that includes both a crest and a trough is called its wavelength, and it's given by the Greek letter lambda. The amplitude is half of the distance from the top to the bottom, or from crest to trough, or it's half of the total spread of the wave away from its equilibrium line. Here it's given by letter A for amplitude, and it just measures the distance from the equilibrium line to the crest in this case, but it could measure the distance to the trough. Down below is something similar attempted for a compression wave or a longitudinal wave. Here, Just like a crest, there is a center of compression, which is where the slinky is squeezed the most. That's where the pressure is the highest in the slinky, or where the coils are packed together most tightly. The opposite of a compression is called a rarefaction, and it's indicated here where the slinky coils are stretched out further. That's also a place of low pressure. The wavelength is from normal pressure to normal pressure through both a center of compression and a center of rarefaction, just like the wavelength here is from the slinky at equilibrium to, again, at equilibrium, where it is passed through all of these phases or states of being, including a crest and a trough. To end our transition into waves, let's take a look. This is the wave equation we're going to derive right now. Suppose the following picture were to pass by you each second. You can see, if you count, that there are 1, 2, 3, 4 complete wavelengths, and each of those wavelengths is 3 feet. There are 4 waves per second passing by, so the frequency is 4 hertz. And each wave is 3 feet long, so the wavelength is 3 feet. How fast are the waves traveling? Insert dramatic pause. If you said 12 feet per second, you're correct. Those waves, each 3 feet long, if there are 4 of them passing by each second, must be traveling at 12 feet per second to pass you in such a way. This means, for waves, the speed is the wavelength times the frequency, or v equals lambda f, or v equals lambda times 1 over t, because frequency and period are inverses of each other. Or, rearranging, lambda equals v times t, which is really just d equals vt for waves.